All right, so in Chapter 4, we're going to return to field extensions, which was something we touched on at the end of Chapter 2. And then we took a little bit of a side journey through vector spaces. I'm going to tie those ideas together. So we're going to go back to field extensions and tie in the vector space stuff that we learned. So just so we remember where we were. A field is a set F. We have two binary operations, addition and multiplication, and a bunch of nice properties worked for those operations. So addition and multiplication were both associative and commutative. There's an additive identity, and we have additive inverses. We have a multiplicative identity, and we have multiplicative inverses for everything except 0. And then the two operations play well with each other. Multiplication distributes over addition the way we're used to. So a field is a really nice set where we sort of have all the things that we like. When we had two fields, so if F and K were both fields and F is contained in K, then we had this thing called a field extension. We'd think of K as a field extension or as an extension field of F, and we would write it with this K over F notation. And that wasn't talking about any kind of division. It was just saying K is bigger, F is smaller. So K is a field extension of F, K over F. So the third thing we want to remember is that when we had this situation, when we had a field K over another field F, we can think of K as a vector space over F. Okay, so that meant F was the scalars and K were the vectors. And the scalar multiplication is just the usual multiplication in our field. So just as a quick example of this, R is a field, and it's a field extension of Q, which is another field, right? So Q is a subset of R, and so R is a field of extension of Q. Okay. When we thought of this as a vector space, we would think of the vectors as real numbers and the scalars as the rational numbers. So R over Q is a field extension, and also R is a Q vector space. All right. So here's our definition. Here's why we care about this. If we have a field extension, K over F, the dimension of K as an F vector space is the degree of the field extension. So it's the same idea, we're just giving it a different language. So in the world of vector spaces, this is the dimension of K as an F vector space, and that meant it was the size of a basis of K over F. Okay. But now when we live in the world of field extensions, we call it something else. We call it the degree of the field extension, K over F. And we have this special notation for it. K colon F is the degree of K over F. All right, so we're going to do some examples of this. So first, let's talk about that R over Q. So R over Q is infinite. The degree of R over Q is infinite. R is an infinite Q vector space. Okay. And we won't talk a whole lot about that. We're going to be interested mostly in these finite extensions. But that was one that is interesting to think about. All right, so one. C is an R vector space. Okay, so when we think about C as an R vector space, our vectors are complex numbers, and our scalars are real numbers. All right, and what this meant was, if we were thinking about a basis, we want to think about a generic vector is of the form a plus bi. And we wanted to think about a basis as I want scalars times vectors. Scalars times vectors. Those scalars are supposed to be real numbers, and the vectors are supposed to be complex numbers. So again, that's scalar is supposed to be a real number, the vector is supposed to be a complex number, and it turns out that the easy way to do this is to make our scalars be the a and the b, and the vectors are 1 and I. Okay, so a basis for C over R is just 1 and I. We can make any complex number as a linear combination of 1 and I using real number coefficients. So the dimension of this vector space is 2, so the degree of the field extension is 2. Okay, let's try another one that's familiar. So Q adjoin root 2 over Q. So this is again a field extension, or Q root 2 is a Q vector space. And remember the basis for Q root 2 over Q. An easy basis for this was just 1 and root 2. We could write every element as a linear combination of 1 and root 2, and so the degree here is 2. This is a degree 2 field extension. Okay, let's do our Q adjoin root 2 root 3 over Q. Okay, so again, I want to think about a basis for Q adjoin root 2 root 3 over Q. And we've done this before. The elements of Q adjoin root 2 root 3, they were the A plus B root 2 plus C root 3 plus D root 6. And so our basis was that 1 root 2 root 3 root 6. And then the coefficients A, B, C, and D, those were the rational numbers. Those were the scalars that we used. And so the dimension here, the degree of this field extension, is 4. Okay, let's do one more. I'm going to add a new page here to do it. All right, one more. Same sets that we've been using, so Q adjoin root 2 root 3, but this time we're going to think about it as a root 2 vector space. Okay, so what this means is we're going to think about a basis for Q adjoin root 2 root 3 over Q adjoin root 2. And so our scalars are going to come from Q adjoin root 2 instead of just from. And so we're going to be thinking about, we're going to write down our basis once we've figured it out. But what we're thinking about is a generic element of our set is A plus B root 2 plus C root 3 plus D root 6. And we again want to write it as this scalar times a vector. Scalar times a vector. And we need to do that as many times as we need to. That's going to tell us our size of our basis if we do this smartly. All right, so remember our scalars, those can be from Q root 2. So whatever goes here is allowed to be something from Q root 2. This is allowed to be something from Q root 2. The basis vectors are what have to be from Q root 2 root 3. Okay, so let's take a look at our generic element and think about how we can pull out some of these scalars in front. So you might notice right here, A plus B root 2, that's from Q adjoin root 2. So we can use that as a scalar. And it's times just 1. We usually have as a basis vector 1. Okay. And now what do we do with this second piece here? So my C root 3 plus D root 6, I can factor a root 3 out of that. And what's left is just C and D root 2. So that's another scalar. C plus d root 2 is my scalar, and I'm multiplying it by the vector root 3. So that's my basis, just 1 and root 3. So I've taken my generic element and written it as scalar times 1, scalar times root 3. So I don't turn out to need any more. My basis has size 2, and so the degree of my field extension is 2.